stretching your legs. And without further ado, I'm very thankful for Juan to give a talk on non-SOS Putinar-like certificates for non-negativity. Please, Juan, the stage is yours.
Okay, thank you, Gordon, and thank you to all the organizers for the invitation. So yeah, I'm going to talk about a non-SOS Putinar theorem for non-negativity, and this is joint work with my student Lawrence Robert and my colleague Luis Zuluaga from Lehigh. So before talking about non-SOS, I want to review a bit about the SOS case, and just to fix some notation, and I'm pretty sure most of you, if not all, are pretty familiar with all that I'm going to say at the beginning. So just think about an introduction to fix some notation. Yeah. So what I'm going to do in the talk is I'm going to fix some polynomials, and then I'm going to fix the basis semi-algebraic set defined by those polynomials, and I'm going to assume that is compact. So I'm interested only in the compact case. And then we're interested in polynomial optimization. So we're interested in minimizing some polynomial function on the semi-algebraic set defined by the G's. And then, well, there is an observation that finding this minimum is equivalent to just solving this problem here, the maximum over lambda of p minus lambda. So finding the best lower bound for p. Actually, it's just the definition of the minimum, yes. And then, well, one can build from that observation is I was going to say quite natural, but I don't know if it is really natural. But for us nowadays, it's natural to think about Lasser's hierarchy. So we say, okay, you fix an R, and then you take this lower bound that is the maximum lambda, the best lower bound that you can find, such that p minus lambda is an expression of this type here, where tau and sigmas are SOS. They are sum of squares. And then in the R cons for the degree of all the terms that I use here. So all the expressions here are of degree at most 2R. Yeah. So this is the Lasser hierarchy. And then what do we know about the hierarchy? Well, we know that this is a sequence of lower bounds. So they are increasing lower bounds on the minimum. And then which can compute each one of these lower bounds using semi-definite programming. And it comes from the fact that every SOS, every sum of squares is SDP representable. And then under mild conditions, we get convergence. Yeah. And I say mild here because I'm already assuming that it's compact. Yeah. And then the mild condition is really that the quadratic model is Archimedean. And the convergence, at least at the asymptotic level, is given by this theorem of Putinar from 93 that precedes Lasser's hierarchy. And is, well, if the quadratic model is Archimedean, notice that being Archimedean implies in particular that the set has to be compact, then every positive polynomial has an expression of this type. And therefore, for some R, the Lasser hierarchy, well, sorry, therefore, when R goes to infinity, I will get that the Lasser hierarchy will give me the right value. So it will converge. Yeah. So this is asymptotic convergence. Lasser hierarchy has been studied a lot, and the convergence of Lasser hierarchy has been studied a lot also in the last decade. So it has been an active area of research, especially in the last decade. So Ni show actually that if you have the Archimedean condition plus some form of optimality conditions, then you get actually finite convergence. And there are other results about finite convergence using some similar extra assumptions like convexity. Yeah. Now, in terms of convergence rates, also there has been some new results from Baldi and Murray, for example, from just last year, that shows that the hierarchy converges in a rate that is 1 over poly of R. Yeah. The previous result was by me and Marcus on showing that convergence of type 1 over log R. And there are also lots of specialized bounds. So for the hypercube, for the sphere, for the ball. And here I just mentioned one from Fun and Fancy, and it's that in the sphere you had convergence of the type 1 over R squared. Yeah. So there are a lot of results on convergence, and there is even a tutorial here in this workshop on Wednesday morning. We can look at, we'll talk about it. So we know a lot about Lasser's hierarchy. And here I'm just picking some of the topics that I'm interested in. So the convergence rates. Now let's look at the numerical performance. So there is a lot of theory, and it's really nice and powerful theory about Lasser hierarchy. What about the numerical performance? So here I bring some examples. So it's just 2 variables, and I have 4 equations, 4 polynomials in the constraints, and all the objective and the 4 constraints are quadratic. So here is a plot of the feasible region. And what I'm doing is I want to find the closest point in the red area to 1, 1. So 1, 1 should be somewhere here. Okay? Probably the optimal is this point here. Okay, so if we do the first level, so we just, I mean, in every level we'll have 5 SOS. And then in the first level, this one is of degree 2 and this one is of degree 0. And then we get that the systems, so the Lacer hierarchy will be written in this format. This is just a linear system of equations, and it's a small one, 6 by 14. And then we need this number of SDP matrices, and it's just one of 3 by 3. And 4 non-negative constants corresponding to this sigmas. And the optimal value that we get is 9.4. Yeah. Now, if we go to the second level, then we get a much better optimal value. So we get a much better lower bound, 36.06. Yeah. The system is much bigger, and then we get also many more SDP matrices. So the same number of SDP matrices, but much bigger SDP matrices. So we still have 5 SDP matrices, but the system is bigger. Okay, so the problem is growing. And well, the size of the problem is going to grow exponentially in R. So if I go to the second level, to the third level actually now, so I will get an optimal value of 51.73, and it's a much bigger system. So you can see here, just the linear system is much larger than the linear system at the previous levels. Yeah. And then if I go to the 4th level, well, it will keep growing, and actually I will get numerical error in the 4th level, and in the 5th level also I will get a numerical error. Yeah. And this is almost true for any, I guess, yeah, for any solver you will get a numerical error there. And so these are the results that I got. So I got 3 bounds, 3 lower bounds, and then I got numerical error, so I couldn't get a bound. Now, to be honest, you don't have to run this problem for level 4 and 5, because when you run level 3, you can also show that this is optimal. So you get an optimality certificate at level 3, and you also can extract a solution at level 3. So you will stop there. Yeah, but if you keep going, you will just get numerical errors. And it's because you have an over-restricted system. So it's natural that you get numerical errors. Okay, so in summary, so what I have said so far is we have a lot of theory, and here I talk mostly about convergence. So the 3 points, the first 3 points about convergence, we have a lot of theory. It's a very well-studied hierarchy, or a very well-studied object, the Lacer hierarchy. Is SDP representable? On the other hand, SDPs, even though they are polynomial type solvable, the level is growing exponentially, so the SDP becomes really expensive. So and people have looked into this already, and then one way to actually make it cheaper, or to be able to do something, it will be, one possibility is to exploit the structure. So we can exploit sparsity when it is present. We can exploit symmetry. You saw those linear systems, they look very symmetry. And also there has been some ideas on doing optimization algorithms to work directly over the SOS con instead of the SDP representation, because the SDP representation is just a lifting of the SOS con. So these are very interesting theoretical ideas. And another idea, and this is where I'm going to move next, is to actually completely ditch the SOS, the sum of squares. So what I'm going to do is we'll replace SOS by other classes of non-negative polynomials. And then what do I mean by that? Well, this is I hope, a motivating example on how can we get non-SOS non-negative polynomials. So if you apply the arithmetic geometry mean to these 3 terms, we will get that the cubic root of the product, and that's x squared y squared, is less or equal than the arithmetic mean, that's the sum of divided by 3. And then from there, we actually get this, the famous Moskine polynomial is non-negative. Yeah, so this is the shortest proof that Moskine polynomial is non-negative, at least the shortest I know. And the interesting property of this polynomial is that this polynomial is not a sum of squares. So this polynomial is non-negative, but it's not a sum of squares. And we can prove the non-negativity using arithmetic mean, geometry mean. So the idea is, well, maybe we can use this type of ideas to construct other non-negative polynomials that are non-SOS. And then if you do that, you get what are called the sunk polynomials. So we can build non-negative polynomials that are non-SOS, and actually the sum polynomials are SOCP representable. So we can use second order optimization to optimize over the sum com. Okay, so this is an idea that has been proposed also probably in the last decade. And there are different classes of non-negative polynomials. So there are the sum of squares, and those are SDP representable. There are also the SD-SOS and the D-SOS. So these are diagonal SOS and scalar diagonal SOS. And these are SOC representable and they are LP representable. So these are special forms or SOS. So these two classes are obtained by limiting the type of SOS that I will use. Yeah, so and then well, they have been used actually in practice to obtain good bounds for polynomial optimization problems. And then also the sunk polynomials that I just mentioned that were proposed also in the last decade to replace the SOS, and they are not comparable. So the first one is the SOS, SD-SOS and D-SOS, they are subsets of SOS, and sunk are not comparable. So if we look at these sets of polynomials, we have the set of all non-negative polynomials, and then we have the SOS polynomials, the sunk polynomials. The SD-SOS are actually in the intersection of these two, and then the D-SOS are here inside the SD-SOS. And then here we have SDP, here we have SOCP if we want to work with SD-SOS. If we work with this SOS, we will get an LP, and with a sum, we can do it with via SOCP. Okay, so this is the classes of sets that I have in mind. So we have different sets of non-negative polynomials, and maybe you have one in mind, also a different one, and then you can just put it in here. And then the idea is, well, now we want to do something similar to Lasserre hierarchy, but using different non-negative polynomials instead of SOS. So what I will do is, you give me a class of non-negative polynomials, for example, one of the previous ones, let's say sunk. Yeah, you give me S that is compact and non-empty, and then I want to solve exactly the same problem, the polynomial optimization problem. Then I can define this bound, and what I'm doing is I'm just taking the same bound that I will get in the Lasserre hierarchy, but I'm replacing the condition on tau and sigma. Instead of being SOS, I will ask for tau and sigma to be in K. Yeah. So what do we have in that case? Well, because K is a class of non-negative polynomials, I still get that these are valid upper bounds. And because the condition that I'm putting here of increasing degree, then I get every time a larger lower bound. Sorry, I said that. So this is a sequence of lower bounds on the minimum that I want to find. Yeah. Now the computation of these bounds is going to be an LP, an SOCP, an SDP, or any other optimization method that depends on the K that I'm using. Yeah. And then the question is, but do I get convergence? Yeah. So before we said that the convergence of the Lasserre hierarchy is quite well understood. Do we get convergence here even in the asymptotic way? Okay. So the answer is no. And actually there is an example by Joss in 17. So if you take K equal the SD-SOS class, yeah. So if we take this polynomial, the simple example, so we have a polynomial P that is x1 plus x2 minus 2 squared, and then we take the ball, so this is just only two variables. Then if you compute the minimum of P on the ball, you get 2 minus square root 2 divided by a square, and this is positive, yeah. But when you apply the hierarchy, the Lasserre hierarchy based on SD-SOS, you will get that the best upper bound that you can get is minus 2. Yeah. So there is a huge gap between the optimal value, yeah, that is positive, and the value that you can get from the hierarchy that is minus 2. Okay, so there is not convergence. And actually, so if you do what I call the naive K Lasserre, that is just replacing by the SOS by K, then this one doesn't converge. And what that really means is, well, if you take the naive K Putinar, that is just taking the same statement of the Putinar theorem and replacing SOS by SD-SOS, that theorem doesn't hold. Yeah, it's not true. Okay, there are other counterexamples. For the SD-SOS and the D-SOS con, we have these two papers, and for the sunk polynomials, the same people that proposed the sunk, they also have shown that if we just replace in the Putinar theorem SOS by sunk, you don't get, and the theorem is not true. Okay, or the statement is not true. Okay, so the question is, how can we build a non-SOS laser type hierarchy? So I want a hierarchy that looks like the laser hierarchy, but doesn't use SOS, but uses other classes of points, and thus has convergence. So what we need is a non-SOS Putinar theorem. Yeah. So the first thing that I want to do is to actually work with the Archimedean assumption. So I want to get a work around the Archimedean assumption, and the simple one, and this is also well known, is, well, if we assume that we have that my set S, because it is compact, will be containing some ball, and if I assume that I know the radius of that ball, so my assumption now is I'm going to assume that I have the radius, so I can write S in this form. Yeah, so it's just the points on the ball. Then I get a theorem like Putinar, where I have this extra term. This is equivalent to just saying, well, if you know an upper bound on the radius, so if you know the radius of a ball containing S, then you can add this inequality, because this is a redundant inequality, r minus norm of x squared bigger or equal than 0, and then you can apply Putinar there, because for that set you have the Archimedean property. Yeah. So here, in that way, it's just a get around the Archimedean assumption. Now, this doesn't solve the problem, because now if I replace SOS by SDSOS here, for example, this statement is not true. And it's because this contrasample that we just saw actually is in the ball. So here, even though I have an Archimedean, a problem for which I have that extra definition or that extra inequality of the ball, here with the SDSOS, the Archimedean doesn't work, as the Putinar theorem doesn't work. Yeah, so this theorem, if I replace SOS by SDSOS, is not true. So we still need to work a little bit more to get a theorem that is true. So the main theorem, or the theorem actually, is how does this Putinar-like certificate looks. Yeah, and then what we need for that is just one definition. We are going to define the class of sums of monomials squares, and I will give a little bit more details in the next slide. So if I take any class of non-negative polynomials containing the sums of monomials squares, yeah, and then I have my same setup as before. I will have S is my semi-algebraic set, and I'm assuming that I know the radius of the ball containing S, and I also need the upper bounds for the G's, for the constraints on the ball. Yeah. Then if P is positive on S, then I can write it always in this format. Yeah, where tau 0 and tau 1 and sigmas, they belong to K, to my class K of polynomials. Yeah, and notice that in tau 0, what I'm doing is tau 0 is a polynomial that depends on all these upper and lower bounds. So I had this is really the ball bound. So this is the polynomial defining the ball. And these other terms, they are just upper and lower bounds on the variables that I get from knowing that they are in the ball, that my set S is contained in the ball. And same with tau 1. So tau 1 belongs to K, is evaluated on all these bounds, and is multiplied by the polynomial defining the ball. And then I have a term similar to the usual Putinar. The difference is that this sigma actually is univariate, and sigma is evaluated in the upper bound minus G. Now, notice that this expression shows that P is positive. It's always good to check that, because all the elements that appear here, yeah, they are not negative on S. Yeah, well, tau 0 and tau 1, they are not negative because they are just non-negative polynomials. This is because S is contained in the ball. This is non-negative, and here U minus G is non-negative. Yeah, and then I know that it's sigma that, and then G is non-negative. Okay, so this is non-negative in S, so this shows that P is non-negative. And then what this theorem says is that we can actually always find such expression. So if we do now the K-laser, if we can do a laser kind of hierarchy using this expression. Monique has a question.
Sorry, Juan, to interrupt, but just to make sure I follow. I mean, you said K of polynomial are multivariate polynomials.
These are multivariate polynomials, yes, but the sigmas are univariate.
But so you wrote and univariate polynomial sigma j in K. So maybe I just
Yeah, so K is a class of polynomials. This is also true for the SOS case, yeah? So tau 0 and tau 1 in the SOS case, there will be sum of squares with 2m plus 1 variables, yeah? And sigma is going to be a univariate sum of squares.
So sigma is not in K, yeah? Sigma j.
Sigma is in K because K is sum of squares. So these are sum of squares. In this case, are sum of squares of 1 variable, of 2 variables, of 3 variables, of 4 variables. Oh yeah, this notation is wrong. I see. It's confusing when I say K. It's a subset. So K is some class. So you should think of as when I say sum of squares, I don't fix the number of variables.
Ah, okay, good.
Okay, so they are not in the same variables as the yeah, yes.
That was
so
my
I'm not fixing the number. I'm not prefixing the number of variables. Yeah.
Thanks.
So when I say, yeah, if I say sum of squares, this will be sum of squares in 2m plus 1 and variables, the tau 0 and the tau 1, and the sigma is going to be just 1 variable. Okay. Okay. So
ask a question.
Yes, of course.
So you the tau here, you say it's is it saying it's in the preordering of the r plus xi and r square minus norm of x square?
No.
So you're saying something more?
Yes, it's something more. So here, because this is it is important here that these functions, these coefficients, they're evaluated not in x but in these other functions, yeah, in these linear expressions obtained from the bounds and the definition of the board. Same here. This one is evaluated in u minus g. Let me think again, because I haven't thought about it from that point of view. But here, because here I don't have products of the g's.
Yes, but I'm talking about the tau 0 and tau 1. The first coefficients you have here.
Tau 0 and tau 1?
Yes.
Oh no, they are just elements of K. So they're, again, if these are sum of squares, for example, tau 0 is just going to be a sum of squares in 2m plus 1 variables. Yeah. So let me go here. Maybe this is more clarifying in this slide. Yeah. Okay. So what happens when I am in this SOS case? What I get is that I can write P in this format. So tau 0 is a sum of squares, tau 1 is a sum of squares, and sigma is a univariate sum of squares. Yeah. Now this implies the usual Putinar, or at least the one that I wrote with the definition of the ball, because tau 0 is a sum of squares evaluated in whatever I evaluated, because if I have a sum of squares and I compose it with another polynomial, I always get a sum of squares in the original variables. Yeah. So now tau 0 is just a sum of is some tau 0 tilde evaluated in x. Yeah. Who is tau 0 tilde is this guy. Yeah. And tau 1 tilde is going to be this guy. This is also a sum of squares because I'm taking a sum of squares of 2m plus 1 variables, and I'm replacing those variables by these linear expressions and this quadratic one. Yeah. And then sigma, also again, this is a univariate SOS, and it's replaced in u minus g. So it's on sigma tilde of x. Yeah. So this tau 0, tau 1, and sigma, they belong to the class of non-negative polynomials that I have pre-selected. In this case, the SOS. Okay. So yeah, they don't belong. So you can think, okay, SOS or SONC or SD-SOS or any of those classes. Yeah. The important thing is that this expression that I have here is going to be linear on the tau 0, tau 1, and sigma, on the coefficients of these polynomials of tau 0, tau 1, and the sigmas. Yeah, because those are going to be my variables in my optimization problem. So this whole expression is linear on those coefficients. It's kind of, I guess the element that we're adding here is we're allowing for compositions. So when we write Putinar or Lasser's expression, usually we say, we take tau 0 of x, tau 1 of x, we do multiplications with other polynomials, yeah? But here we are allowing to have compositions, and that's the key element. Actually, that's what it says here in this remark, yeah? When you do the SOS case, you can drop all these compositions. You can put them hidden in here. But when you are working with some other classes, for example, the sum class, that one is not close on the composition, and therefore you have to keep the expressions as in this one. We cannot say that this polynomial, tau 0 evaluated, composed with all these linear polynomials and this quadratic one, is a sunk polynomial. So if tau 0 is sunk, my tau 0 tilde might not be sunk, and that's why we needed to write it in that way. Does that answer your question, Bernard?
Yes. Okay.
Okay.
Thank you.
Good. Yeah. So, and then I guess what also a key point is that here the only assumption that we have on K is that K contains the sums. Sums are the sums of monomials squared. So are just expressions that I can write in this way, where the coefficients are non-negative. So I'm just having monomials squared. So that's why I have the 2 alpha here, and then non-negative coefficients. So all the sums, they are contained in the DSOS, and therefore they are contained in all the classes that I mentioned before, and also in the hyperbolic polynomials and psi-aj polynomials that I haven't even mentioned before, so that I haven't put them in this. Okay, but these are very simple expressions that they are contained. I mean, I guess it's natural to include them in any non-negative class of, or in any class of non-negative polynomials. Yeah, so it's just I have monomials squares, and then I combine them with okay. So this theorem, so that implies that this theorem, our main theorem, already shows the Putinar-type theorem for songs, for SDSOS, for DSOS, for SOS, that is already known, yeah, for SAC, for hyperbolic, yeah, for any class of non-negative polynomials that contain sums, this theorem is going to be true. Okay, and then, well, because the theorem is true, now we can define the K-Lasser hierarchy. And then if you want to get convergence, at least in the asymptotic version, well, a natural way to do it will be to do it in this way. So notice again, we put here the tau 0 composed with these expressions, tau 1 composed here, sigma evaluated here. And then the taus and the sigmas are in K. Yeah, again, K might be SOS, sunk, SDSOS. Yeah. And then we get that is a sequence of increasing lower bounds, and they converge to the optimal one. Okay, and that's of course a corollary of the K Putinar-type. Okay, so let's revisit the sample, the countersample that we gave before. Why we don't fail here now? Well, again, our P is this one, S is the ball. Yeah, and notice that P is actually a DSOS polynomial evaluated in 1 minus x1 1 minus x2. Yeah, so this is actually sigma of UB is just U plus B squared, which is DSOS. Yeah, so if I evaluate, I didn't write it here, sigma of UV is U plus B squared. So that's a DSOS polynomial. So when I write it in this format, when we use this Lasser hierarchy this way, the DSOS Lasser hierarchy, well, we just get that from the first, I should have to call it tau. From the first tau, we will get that this polynomial is bigger, we will get the right value for this. Okay. Okay. So we know, now we know that we have a Lasser hierarchy for any class of non-negative polynomials containing sums, and we know that it converges It has, because we have the K-Putinar theorem. And so, but for the Lasser hierarchy, there was all this nice theory, and then actually we also can show convergence rates, and I'm going to do that next, and that's related to obtaining degree bounds for the expression that we have. So I'm going to explain how to obtain those degree bounds. We want to look at the finite convergence, so that's something that we haven't think about yet. So that's a to do. And then also one thing that we have is there is this sparse version of Putinar that will give a sparse version of Lasser theorem. And we also have a sparse version of Putinar theorem. So I'm going to also explain that next. And then there is a symmetric version, and also that's a to do. Okay, so this is comparing the list of what we know for the Lasser hierarchy. For in the SOS case, many things can be translated for any K, while containing the SOS polynomial. So what I'm going to do now is actually I'm going to look a little bit more in detail to the proof of the Putinar theorem, and then that will give us a hint of how to do the degree bounds, and also the part of the sparse Putinar, the sparse version. Okay, so that's the second part of the talk. But I don't know if there are more questions on the first part.
Yes, can you hear me?
Yes.
Okay, this is Lorenzo Baldi from India, and I wanted to ask you some questions about the theorem with this K. Do you relate this result of this general Putinar with other results in real algebraic geometry? If I'm not wrong, the name should be like Jacobi theorem, when they represent positive polynomials, but not with some square coefficients, but with other coefficients. I don't remember exactly the conditions. They are a bit technical. There is like quasi-preordering or quasi-pre-prime. I don't remember. You can find this theorem in, for instance, in the book by Marshall.
Oh, so I didn't hear you well at the beginning. So you're asking me whether it follows from that kind of result, or...
No, I'm asking if this result can be obtained as a corollary of this other result by Jacobi, or if this is another type, you don't satisfy these conditions that are sufficient, that are less general than being without having some square coefficients.
These are I don't think it will follow, but yeah, you know, I wouldn't think it will follow, and it's because this result has a kind of a different structure, here in this evaluation.
Okay. And about the structure, I see that you use R minus X and R plus X, and then you use the quadratic the Bohr constraint. But can this be simplified, since that this linear expression can be written in the quadratic module of the Bohr that you use? Or it's not?
So the point is, if you use for SOS, this is all simplified. This is what I did in this slide. But when you use different cones, like the sunk cone, when tau zero is a sunk polynomial, tau zero evaluated in this first polynomial I have here is not sunk, so I cannot simplify it.
Okay. Thank you for the answer.
Okay. So I saw that some people cannot hear what we were saying because of the noise. I will repeat a bit. So the question was whether one can simplify this expression here, and then the point. This is a very important point here, so I want to repeat that part. And is, if we are working, for example, with sunk polynomials, so the fact that tau zero is a sunk polynomial, it wouldn't imply that tau zero evaluated at this expression here is a sunk polynomial. So it's very important that we had this evaluation, we had this composition here explicit. And that kind of also relates to the other question that was whether this follows from some other results. And I will say that I think it doesn't, and it's because, well, those results don't have this kind of composition. So, and this is for certain classes of polynomials. So again, maybe I should go here. Again, I'm working with not just SOS, but I'm working with some subclasses of SOS. and when sunk polynomials that some of the sunk polynomials are not SOS, like the Moskine polynomial. Yeah, and then the point is that sunk is not closed under composition. So when I write this expression, I cannot claim that tau 0 tilde here, where that is just this composition, will be a sunk polynomial. Okay, so in general, it will not be. Okay, so I will move to the second part, and then the second part will start with the proof. So I had I want to review quickly the proof. And actually, the proof idea is simple. So what we do is first we move from S, from the negativity over S to the negativity over the ball. And the idea to do that is, well, if you give me P that is positive on S, then I will build univariate polynomial sigma in K, yeah, such that when I take this expression here, so here I'm evaluating H sigma on U minus G times G, this is going to be positive on the ball. Therefore, to show that P is positive on S, I just need to show that P minus this is positive on the ball. So I move the problem from the set semi-algebraic S to the ball, because in the ball I will have more structure. And then actually this is not so difficult. The point is one has to show that sigma T equals C times T to the do D works. And then this is just, well, picking carefully C and D large enough. And this actually resembles the proof of Mia and Marcus in 2007 for the complexity of Putinar. Yeah, so that's the first part. We do that. And then also, well, also in that part, we also can compute who is C and who is D, at least give bounds, and that's going to be important for the degree bounds. So we know D, we can give bounds on D in terms of the data that we have for the problem. Okay, and then the second part is actually we have to write the K Putinar certificate on the ball. Yeah. So now we need to show that if P is positive in the ball, P will be in this case this expression. So if P is positive in the ball, then there are 2n+1 varied polynomials, tau 0 and tau 1 in K, such that P can be written this way. So this is just the K Putinar certificate in the ball. So from the lemma 1, we reduce all the theorem to the ball. And then to do that, we use a result from that we have with my former student, and is if P is positive in the ball, then I can write P in this format where F has non-negative coefficients. Yeah. So here we use this even weaker bounds. Yeah. This linear bounds here, and again the ball expression. Yeah. Now from this expression, we can message this expression to obtain that P actually can be written in this format, where G is a polynomial, yeah, in 2n+1 variables with non-negative coefficients. And actually, this is the messaging that has to be done. It's just using this expression down here. So it's just basic algebra what is needed to be done here. We get this. And then now, if I have a polynomial G that is written in terms of the squares of R minus xi and the squares of R plus xi, and I mean all of them. So, and then the ball definition, yeah. Then I can write G as tau 0 or this, where this is a sums. So it's just a sum of monomials squares, plus tau 1, where I have this extra term here. And what I'm doing is I'm just taking all the monomials where this one is of even degree, the R square minus norm of x squared is of even degree. I will put it in the first, in tau 0. And the ones where this is of odd degree, then I extract 1, I factor out 1, this R square minus x norm of x squared, and then that will give me the tau 1. Because then all the terms have even degree, so they are just a combination of monomials squared. Yeah. And because G has no negative coefficients, tau 0 and tau 1 are in sums. Yeah. So this proves the second part. And then why I'm showing this proof, because I'm interested in getting degree bounds. So with Lawrence, now we have degree bounds for these expressions. And the degree bounds are really just by working out the proof. So we know that we can bound D and C here in the lemma 1. And then we know we need to go and bound the elements that appear here in this proof. So the second part is just algebra. So this is not increasing the degree. Yeah. And then we need to bound this degree here in F. And then we had to look at the construction in this old paper of F. And then by doing that, we use Polya theorem, and then we get some bound. And actually, that bound is similar to the bound of me and Marcus from 2007. And so we get something that is order 1 over log R. And if we add some assumptions, we can get a bound similar to the Baldwin-Wright bound of 1 over poly R. Yeah. So these bounds are really about getting degree bounds for the Putinar theorem. So that's what is called an effective version of the K-Putinar theorem. And as I said, they are just done by analyzing carefully the constructions that we use in the proof. Yeah. So these are similar to actually these 2 existing papers for Putinar, but the constants are more worked off, and the analysis is a little bit more complicated because we are not working with sum of squares. Okay, so those are the degree bounds, and I want to move to the Sparse certificates, but if anyone has questions, I think I can also answer questions about the degree bounds here. Okay, so I'll move to the Sparse certificates there. And now is basically what I want to do is to give a sparse version of this K-Putinar theorem that is going to be similar to the sparse version of Putinar theorem that exists. And those sparse versions actually of Putinar theorem are used to construct a sparse SOS certificates that have assured convergence. Yeah. And the idea is if we have a sparsity, then we can exploit this structure to have, in the case of SOS, smaller SDPs. In the case of SONC will be smaller SOCPs, or in the case of SD. So we can exploit the sparsity. Yeah. So what do I mean by sparsity? There are 2 types of sparsity that we consider. One is term sparsity, and that is similar to the sparsity that Jean Bernard was talking in the previous talk, and is when you have a polynomial, for example, evaluated in few terms. So notice that in our expression, the sigma j uj minus g is term sparse. If I want to represent this here, sigma j is the variable polynomial, is univariate, and I only need, well, the degree plus 1 variables. Yeah, a univariate polynomial has only degree plus 1 coefficients. So I only need that number of variables to represent this expression. Yeah, it's going to be a big linear expression, but only has this number of variables. And this is independently of the structure of the P and the G's. So for this part of the sparsity, I don't need to worry about whether P or G, they have some sparsity structure or not. We can always use it. Okay. And then another type of sparsity is correlative sparsity. When I can write, for example, if I have P in 3 variables and I can express P as P1 and P2 only in 2 variables each. And then if to check if P I mean, if P1 and P2 happen to be non-negative, then P is non-negative. Yeah, and P1 and P2 use less variables. Yeah, so that's a way to actually take a large problem and make it into a smaller problem. Yeah, and then what we're going to do is actually in the K-Putinar, the terms tau 1 and tau 2, that they come from the ball. And we want to show that we can do that in such a way that they obtain the sparse structure present in P and G. So this second part, we only need to worry about the ball because it's about tau 1 and tau 2, but we will need to worry about the sparsity structure on P and G, meaning if P and G are full, if they don't have any kind of correlative sparsity, if I cannot write them in this way, then I won't gain anything. Now for that, I need to introduce first the correlative ball. And the idea is this is a ball that is really the intersection of several cylinders. So in this case, I have 3 variables, and I have x and y, and I have y and z in different sets of variables. And then this is the intersection of the cylinder, the xy cylinder and the yz cylinder. Yeah. And then this is what I'm going to call, this is going to be my ball, my correlative ball. And then the theorem in this case will look in the following way. If you have a polynomial that is correlative sparse, so I can write as P1 of xy plus P2 of yz that is positive on the ball, then this polynomial can be written actually as P1 tilde of x and y, P2 tilde of y and z, where each one of them is positive on the smaller ball, yeah, on the ball with less variables. So if I want to check whether P is positive on the ball, I need to find P1 tilde and P2 tilde that are positive on each one of the respective balls such that they add to P. Yeah. So, but for this, I need to know that P has this structure. If P doesn't have this correlative structure, I will never do it this way. Okay. So this is for the case of only 2 balls. Yeah. If I want to have more than 2, so if I want to go to K balls, I need to do some induction. And for that, to be able to do that induction, I will need some extra structure in the way of the indexes of the variables, of the subsets of the variables. And I need the running intersecting property. And what it says is, well, I have my indexes of variables. So here J is the set of variables that I'm considering. So I will have each polynomial G, for example, in a different set of variables. Yeah. And then the union of all of them cover the whole N. Yeah. And then for each I have the property that my last set intersected with all the union of all the previous sets is completely contained in one of them, in one of the previous sets. So that's the running intersected property. And this is just to do induction. So we're going to use this proposition and we are going to do induction. And then if we have this property, it's pretty straightforward to do it. And then what happens is we generalize the previous proposition from 2 to K. So if I have P has this correlative sparsity and is positive on the ball corresponding to this indices, so the xj are going to be less or equal than R for L equal 1 to K. Yeah, we get this ball. Then I can write P as a summation of P hats where each P hat is positive on each one of the balls. Yeah. So from this, we get a K Putinar theorem that with a sparsity. And that means we basically get the same expression, but now what we have is a summation of expressions over each ball. So here for the L ball, we're going to include only the G's that have variables in that ball. Yeah. So here the kind of sparsity that I'm assuming is P has that correlative sparsity, and then the G's, the variables in G belong to one of the set of variables. Yeah, so that's the kind of sparsity that I need. Okay, and then we have this sparsity that this is just a generalization of the same SOS Putinar sparse theorem. Yeah, the Lasser and co-authors have used to obtain a Lasser hierarchy that is sparse, to exploit sparsity in the case of Lasser hierarchy. Yeah, and then we can get all the taus and all the sigmas are, well, the sigmas are always sparse, and then we get that the taus are also sparse in the sense that each tau will depend on just few variables, the variables in each of the sets. Okay, and then the sparse K Putinar has the same assumption as the general K Putinar, and is that K should contain all the sums, so it can be applied to all these sets of polynomials. Okay, and then if there are questions on the sparsity or anything else, I can answer, because this is basically the end. So what we did was we showed this generalization of Putinar theorem that works not only on SOS but in any set of non-negative polynomials containing the sum of monomials squares. And then the approach is, well, we reduce proving non-negativity on a semi-algebraic set, on a compact semi-algebraic set, to proving it over the ball. And then this allows us to, because this approach is quite constructive, we can build degree bounds, and we can also do a sparse version also, because this separation between, we reduce to the reduction to the ball is always a sparse, and then we show a sparse version for the ball. Okay. And well, we expect that this closes the gap between the application of the SOS and the other classes of non-negative polynomials.
Thank you very much, Juan, for this very nice talk. I'll open up for questions. Please unmute yourself and ask a question if you want to.
Hi, hello, can you hear me?
Yes.
Yeah, many thanks for the nice talk. So in practice, how does it work? Do you have to go very high in the hierarchy to get the same bounds, or do you have like practical degrees similar to the usual Putinar?
So in practice, we haven't used our hierarchy in numerical experiments like in big ones. We only did it in small ones, and then the bounds are similar depending on exactly what. Of course, it depends on which K you take. Yeah. Now, in practice, there are if we look at the naive Putinar, yeah. So the naive K-laser, where you just replace, have been used in practice to solve big problems. Yeah. So yes, our expression is different. So maybe the bounds are weaker, but that's the next chapter of the thesis of my student actually to do all this practical stuff. Yeah. Okay, so we did it for small problems and it works well, but we don't know in the large ones how it works.
Because you know that so there are all these large-scale problems coming from the optimal power flow, for instance.
Yes. So for example, for optimal power flow, this naive K-laser with SD-SOS has been used. Yeah. You also have some work on using SOS with sparsity. Yes.
Yes. So yeah, the TSOS works well on some instances, but there are still a lot of instances with big gaps to optimality. Yes. And yeah, maybe this technique could provide better bounds.
And then yes, and then Bisangadar and Luis Zuluaga and co-authors, they have worked on using this but it was like with this form, this naive K-laser with SD-SOS, and they also get good bounds. And then for other instances also it was big gaps, but for some instances were very good bounds.
Okay.
So we want to implement our hierarchy with that is similar to this one, but it's different. Yeah. So we need to check.
Okay.
Okay. Thank you for the question.
Hi, Juan. Thank you for the nice talk. So I was wondering, in the K-Putinar theorem you have, you introduce a lot of variables that mirror and shift the variables. But like the R minus X and the X minus R. But if we instead take the cone we're working with and close it under these operations, like under all shifts on the axis and all mirrors along the axis, maybe we can do it more efficiently that way. Like for the song cone, I would imagine that it might be relatively easy to close the cone under these operations.
I mean, to take all the compositions and looking for the K-Putinar theorem here. Here, yeah, you mean to close to under all these compositions. That could be a good idea. The question is because these are linear transformations. So these are let's say in the song cone, these are 2n+1 variable songs. And then if you close it under these compositions, then now you get n variable polynomials that are non-negative. Yeah. I guess the question is, how can we express that closure if that can be done efficiently? Yeah, because now you're getting something larger than the sum cone in n variables, let's say. Yeah. Yeah, but that sounds I guess you know how to do it, yeah, now because you're asking the question or... But okay, because that would, yeah, if that's possible, then that would be more efficient, definitely.
Can I ask a question?
Yes.
So I'm trying to connect different representations in my head because now there are so many. So if you think about Schmidtgen, so in Schmidtgen, you have the powers of the GJs, right?
Yes.
I mean, you multiply them. So here you don't really do that. because you take powers of each GJ when you evaluate this univariate sigma, right?
Yes. So sorry, if you take powers, well, if you want to do a smoothing, or you take powers of GJ,
yeah,
then actually you can put here just a scalar, a non-negative scalar.
Yeah, exactly.
And then that, yeah, you can also obtain a representation like
Yeah,
that.
no, so yeah, it has also the flavor of Kriving-Stengel or Handelman certificate, because you have these powers of GJ with when you evaluate sigma.
Yeah.
But you don't multiply them. You don't multiply some GJ with the others. You just take powers, actually.
Oh, I see. Yes. So this is just powers of GJ. Yeah.
So that's,
okay, yeah.
that's messy than Schmidgen, where you need to multiply everything.
Yes.
Yeah.
Yeah, so you can really think of this is I mean, this expression sigma uj minus gj times gj is just a polynomial on gj.
And yeah, and also a practical question. So actually for uj, well, you can just take a naive bound, right? Because you are on the sphere, so.
Yes, because you know that it's in the sphere, then if you know the coefficients, you automatically can compute that.
Yeah. But I guess the performance of the algorithm in practice might be better if you have an accurate bound on uj, right?
Probably, especially numerically, yeah, because the naive bound usually is pretty large, so you get some numerical issues.
And of course, you might not want to do polynomial optimization to get a good bound on uj.
That could be an idea, but I mean, it's a bound on the sphere, but yeah.
Yeah.
May I ask a question?
Yes.
So here the sigma j, you take them, so say in practice, or so you take them as sum of squares, or you really
sigma j? No, these are just any cone. So you give me a cone of polynomials that are non-negative. Yeah. And then I replace sigma, but sigma belongs to that cone. So this could be a DSOS, so it could be a sunk polynomial, depending on the cone that you're working with.
Okay. And
so the simplest one could be this sums cone, yeah. So it's just sum of monomial squares, but it could be, yeah.
And so you should the same for the sigma j and the tau 0, tau 1, because it seems that, for instance, for tau 0 and tau 1, you could take just positive sum of monomials.
Actually, we do show. That's yeah. You can take you can take something, for example, with positive sums of monomials.
For tau 0 and tau 1, with this. And yes, and for sigma j also.
Yeah, possibly this can be extended. So for example, we show that this also works with something that is called H polynomials, and those polynomials are not non-negative everywhere. They are just non-negative on the non-negative order. Yeah, and we also show that this works for that polynomials, for those polynomials. So this works for any set, for any family of polynomials containing all these sum of monomial squares. But
okay. Thank you. And what about the quality of the bounds or exactness of the representation?
Okay, so that exactness we have no clue. Yeah, so we haven't looked at it. So that's and I think that's kind of the next natural question. And the quality of the bounds, as I told Victor, we run some small samples, and it's pretty similar to those small ones. Yeah, if of course it depends on which cone you take. Yeah, because at the end of the day, it's like, okay, if you take so when you go here, well, if you take DSOS, you are considering many less polynomials than if you take SOS. So you expect to have lower quality in the bounds. But in many instances, you can still solve. So I guess at the end of the day, the way we should look at this is, well, of course, if I take DSOS, the quality of the bounds will be lower than if I take SOS. But then the hope is that if I take DSOS, I should be able to solve larger problems. Yeah, because some, well, we don't know. I mean, there are papers where they show that using some polynomials, you can get better bounds than SOS and vice versa. Yeah. But I guess the way we present, the way we think in our results is more like, okay, you take your favorite cone, and then you can apply this kind of technique, and then you know that it's going to converge. And then the question is why do you pick that cone? And then maybe if you are maybe you want to do SOS because you want to solve STPs, or maybe you don't want to solve STPs because the number of variables is too high or something like that, and then you want to use other class of polynomials. Yeah, but basically the way we see our results is we didn't want our results to be limited to just one particular cone. It's like, okay, now as an optimizer, I can come and decide which cone do I want to use depending on the problem I'm solving. So it's a balance between quality and efficiency. Yeah.
Yes. Thank you.
Okay.
May I ask something?
Yes, of course.
So first a question. So do I understand correctly that one of the main tools you use, at least you had two steps in the proof of your K Putinar. First, you reduce to the ball.
Yes.
And then once you're on the ball, do I understand correctly that the main results you are, existing results that you are using is Polia? Is it correct?
For the degree bound.
I mean, to show.
Yes. So this theorem here that we use to write this expression, yeah.
Yeah.
This is a paper with Olga, and then the main tool there is Polia to get that this f has two negative coefficients.
Okay, that's just try to grasp so that's Polia.
Yeah. So basically, we write that we write P as some copositive expression, and then we use Polia.
Okay.
Yeah. So that's the way it works there, and then that's why we get a degree bound there.
Okay, thanks. And maybe a remark, so going back to this question of what you were just discussing before about the computability of the bounds.
Yes.
So maybe now, indeed, so you have a univariate sum of square evaluated at G. So then if the sum of square has a high degree, then you will have to take powers of G. And if G has many terms, you may get some complexity there to evaluate all these powers of polynomials.
Yeah, so the linear system will have because you have this linear system, and then well, it depends how you write it. So when we have used this expression with for SOS, and then we have used it actually even in problems that have not sparsity, because then, I mean, this is still a univariate even if the problem has not sparsity. And then you get some savings even for SOS. Yeah. Yes, here when you write this linear system, you still have to consider monomials. So you have to still equate the coefficients. One way will be to equate coefficients, and you need to still equate coefficients of high degree. So you might have few variables and lots of coefficients and lots of equations. Yeah. But this part will give you a lot of variables. Yes, so that's true. Yes, so some complexity comes there.
Okay.
But, yeah.
Thanks.
But this is the same. It's very similar to the sparse expressions for SOS. It's the same structure, the same sparsity structure.
Are there more questions? If there are no more questions, let's thank Juan again for this interesting, beautiful talk.
Okay, thank you to all.
From Tilburg. So at least some people are in Tilburg.
Yes.
Very nice. And so this was our meeting for today. But please, remember, tomorrow morning we will start again at 9:30 Central European time. So I think we're all in the same time zone, but just to remember, 9:30 in the Netherlands. And I'm looking forward to seeing all of you back tomorrow.